Okay everyone, here is our lecture video for section 10.1, use properties of tangents. Yes, we've used the word tangent before when it came to trig, but now we're going to start talking about tangents of circles. Chapter 10 is all about circles, as you guys have come to find out. So just to start, we're going to review some of that vocab. Definition of a circle: the set of all points in a plane that are equidistant from the given point called the center of the circle. So equidistance means same distance. Our notation for a circle, very similar to how we talked about parallelograms and triangles. A circle with center P is called circle P and can be written as, we just draw a circle with a little center and then whatever we're calling it, so in this case it's P. So just like we used a triangle or a little parallelogram, same idea with the circle. A radius is a segment whose endpoints are the center and any point on the circle. So that's this red line over here. So it goes from the center to the edge of the circle. And remember, the radius is always congruent no matter where it is in the circle. A chord is a segment whose endpoints are on the circle. So this segment can be anywhere in our circle. The endpoints are just on the edge of the circle and it's connected. And then a diameter is a chord that contains the center of the circle. So it's a segment with two endpoints on the circle, but a diameter has to go through the center. And that's just kind of reviewing some vocab that we did earlier in the chapter. A little bit more here. These are probably a little bit newer, something you may have not known already. A secant is a line that intersects the circle in 2 points. So kind of expanding off the idea of a chord. Now we're just talking about a line, so it has two arrows, it goes through the circle. And then a tangent is a line in the plane of a circle that intersects the circle in exactly 1 point. So now we have this tangent line that's going to always go across the edge of our circle and intersect at exactly 1 point, and we call that point the point of tangency. And we also sometimes refer to tangent segments or tangent rays. The main idea here is that a tangent only intersects the circle at 1 point, and it's always going to be along the edge of that circle. So let's try to use some examples using that vocab here. So we're tell whether the line, ray, or segment is best described as a radius, chord, diameter, secant, or tangent of circle C. So for part A here, we have segment AC. I know it's a segment because it doesn't have arrows on our little notation here. So segment AC, AC, well, that's going from the center to the edge of the circle, so that's going to be a radius. Segment AB connects 2 points on the edge of the circle through the center, so that's going to be our diameter. Ray DE, I know it's a ray because it only has one arrow. Ray DE is going to be a tangent. And because it only intersects at 1 point on that circle, so that's a tangent. Line AE is going through 2 points on the circle, so that's going to be a secant. And that's just kind of using some of that vocab there that we did last week. So why don't you guys go ahead and pause the video, if I can get the paper, and try this guided practice example on your own. You're using the same circle from that last example. Try it on your own. All right, in example 1, what word best describes segment AG? Looking at this circle up here, segment AG intersects at 2 points on the circle, but not through the center, so that is going to be a chord. And then segment CB goes from the center to the edge of the circle, so that would be a radius. And then for number 2 here, in example 1, name a tangent and a tangent segment. Well, a tangent is going to be a line. So looking at that, we're going to look for a line that goes through just 1 point on the circle. And that line is going to be line DE. And remember, our notation for a line is we use 2 arrows. And then line DE. And a tangent segment is we don't want arrows. So in this case, we're going to have to use DB as our tangent segment because we want 2 endpoints. And that's being really picky. We won't be getting that picky too often, but that's just making sure you guys know your vocab. So then moving on to example 2. Now we're going to talk about lengths. Find the lengths and circles in the coordinate plane. Use the diagram to find the given lengths. So it's going to be a lot of counting. It may get to the point where we need distance formula, but most of the time it won't. So for part A, the radius of circle A, well, we know the radius goes from the center to the edge of the circle. So this line right here would be our radius, and that's just going to be 1, 2, 3. So our radius would be 3. The diameter of circle A, well, we know it's going to be double the radius, so automatically we can say 6, or we could just count. We go through the center, edge to edge of the circle, 1, 2, 3, 4, 5, 6. Moving on to circle B, the radius of circle B, again, we can just count 1, 2. And again, the diameter of circle B is going to be double that radius, or counting all the way across, 1, 2, 3, 4. So that's pretty easy, not too bad. So why don't you guys go ahead and pause the video again and try this guided practice on your own. Let's pull up the circles here. There we go. All right, use the diagram in example 2 to find the radius and diameter of circle C and circle D. So let's start with circle C here. So the radius of circle C. Well, circle C is the green one in my picture, so it's the larger circle. So our radius here is going to be 1, 2, 3, which means our diameter of circle C is 6. And then moving on to circle D, the radius of circle D, well, that's the smaller black circle here, so it's going to be 2, and our diameter of circle D is going to be 4. And again, that's just kind of knowing the radius is half the diameter is double the radius, and you can get pretty far with that. So then we're going to keep moving forward. A lot of that should have been review. Now we're going to talk about coplanar circles. We've used this word coplanar before. Just means same plane. And the options we have are 2 circles can intersect at 2 points, 1 point, or no points. And this tangent comes back again. We're going to use this word a lot. Tangent circles are coplanar circles that intersect at exactly 1 point. So just like a tangent line intersects a circle at 1 point, tangent circles intersect at 1 point. And you can see this example right here where they're intersecting at 1 point. And then concentric circles are coplanar circles that have common centers. So basically, they're circle within circles, and they just share the center. So they're not actually touching. They don't have a point of tangency. They just have a common center, and they don't have any points of intersection. So then using these definitions, we have something called a common tangent. And a common tangent is just a line, ray, or segment that is tangent to 2 coplanar circles. So it's just a line connecting 2 points of tangency. And we can actually draw these common tangents. I'm going to get out a ruler so I can make straight lines. And we have a few different options. So part A over here, our circles have no points of intersection. They're not touching. If we're drawing that common tangency, I always like to start on the top and bottom of the circle first. We have this common tangent that's at the top of the circles. We have this common tangent at the bottom of the circles. And then we also have this cross tangent right here as well. And again, it still just intersects the circles at 1 point. We also have the other direction. And that's kind of like our complex one. We got our 4 common tangents right there. This is our most complex one. Moving on to part B. Again, I'm just going to start the top and bottom of the circles. There's 1 common tangent. Here's another common tangent. And this time, since our circles are actually intersecting here, we aren't going to have two common tangents that cross. We just have the one common tangent that goes right between the point of intersection, so right between the middle. So this one has three common tangents. And then part C here, again, let's start at the top and the bottom of the circle. Got 2. And this time, since our circles are overlapping, we can't draw that middle common tangent because it would go through more than one point. So this one just has 2. And you're going to see that this pattern happens a lot. If we have 2 non-intersecting circles, we're going to have 4. 2 circles intersecting at exactly one point, we'll have 3. We have overlapping circles, we'll have 2. And then a case where we're going to have 0 common tangents, excuse me, is we're going to have a circle within a circle. This would have 0. So that's just an example of each. We won't do a ton with this, but it is good to know. So we're going to keep moving forward, and we're going to get into our theorems for this section. Our first theorem here is, in a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at its end plane. So looking at this picture right here, to see if this is actually a point of tangency, we're going to see if this is a 90-degree angle. And there are a few different ways that's going to come about, but the most common is we're just going to use Pythagorean theorem to see if a right triangle is created. So take a look at example 4 here. In the diagram, PT is a radius of circle P, is ST the tangent to circle P. So basically we want to see, is this a 90-degree angle right here is what we're going to try to show. And we're going to end up using the converse of the Pythagorean theorem. Basically we're just seeing, is the Pythagorean theorem true? Is it a right triangle? Looking at this, we just have to find our A, B, and our C. Well, this 37 is going to be our hypotenuse, so that's going to be our C. And we know the A and the B don't really matter. So as a little refresher, our Pythagorean theorem is A squared plus B squared equals C squared. Well, if we said A is 35, we have 35 squared plus 12 squared equals 37 squared. And we just have to see if that's true. So 35 squared is 1,225, 12 squared is 144, 37 squared is 1,369. Adding these together, it does indeed equal 1,369. So yes, ST is tangent to circle P. And that's kind of that. You're just going to use that converse of the Pythagorean theorem to work through those, that A squared plus B squared equals C squared. The biggest thing to remember is that your C, your hypotenuse, is always going to be that longest side across from the 90. So let's beef that up a little bit, take it a step further. In the diagram, B is a point of tangency. Find the radius, R, of circle C. So what's in red in this picture right here is actually our radius, and we know this radius is congruent all around the circle. So then to see if it's a point of tangency, we need to prove that's a 90-degree angle right there between the tangent line and the radius. So looking at this, here's our hypotenuse from A to C. B to C is R, A to B is 80, so that's our A and our B. So that's easy for the A squared plus B squared part. We have 80 squared plus R squared equals, our C here is actually 50 plus R. All of that together is 50 plus R squared. And it's really important to use parentheses here because if we think back to Algebra 1, we probably haven't done this in a while. These parentheses right here tell us we're going to have to FOIL. Hopefully you guys remember foiling a little bit. So I'm just going to rewrite our little equation here. 50 plus R squared is the same as writing 50 plus R twice. So then from here, if we FOIL, we do our first, which is going to be 50 times 50, which is 2,500. So there's our first. Our outsides is going to be 50 times R, which is just 50R. Our inside is going to be, again, 50 times R, so plus 50R. And then our last, R times R, that's what gets us our R squared. So hopefully you guys remember doing this from algebra. If not, maybe find some videos talking about foiling, how to foil. They'll go through a lot of examples. So just cleaning this up a little bit, 80 squared is 6,400 plus R squared over on the left side. So then we have 2,500 plus 50R is just 100R plus R squared. So then we just start solving from here. I'm going to subtract the R squared from both sides, which is nice because that's 0 and that's 0. They just cancel each other out, which is good. Now it just turns into a two-step equation that I know you all can solve. We subtract 2,500 to get 3,900 equals 100R. Then we'll divide by 100 to get that R equals 39. And that's the hard examples when it comes to seeing if it's actually a point of tangency. The big thing here is you have to remember to put it in parentheses and FOIL so that you can get your R squareds to cancel. Because that should be happening for all of our examples we're doing in this class. So again, don't be afraid to show all your work. Try not to skip steps until you are really good at it. Then you can kind of start skipping steps here. To keep moving forward, we have one more theorem to talk about in this section. This one's a little bit easier than the last one. It's about tangent segments, and tangent segments from a common external point are congruent. So say we have these two tangent segments over here, and they start at this common point S. It's always going to form an isosceles triangle. So whenever we see this, these two tangent segments connecting at one point, we know that these two segments right here are going to be congruent. So we're just going to set them equal to each other. So trying this example, RS is tangent to circle C at S, and RT is tangent to circle C at T. So they share that common point R. Find the value of X. Well, we know if they share this common point and they're both tangents, that these guys are congruent. So we could say 28 equals 3x plus 4. And from here, we're just going to solve for x. So we would subtract our 4 to get 24 equals 3x. Divide by 3 to get that x equals 8. And those tend to be a little bit easier. Oops, can't see it. Those tend to be a little bit easier. Just set them equal to each other if they intersect at that common point. So our last little bit for this video is some guided practice. Why don't you guys try these on your own, pause the video, come back and check your answers when you're ready. Okay, number 7, is segment DE tangent to circle C? So we got to see if this guy right here is a 90-degree angle. What's a little bit tricky about this one is that CE isn't 2. Just from this outside point of the circle to E is 2. But we know that if C to D is 3, that C to this point right here that I drew in is also 3, making CE 5. So that one was a little tricky, so hopefully you guys caught that. And then that turns into 3 squared plus 4 squared equals 5 squared, which hopefully we know that's a Pythagorean triple, but we can also do our math to show that yes, it is a tangent because it is a right triangle. Number 8 is like the other example we did. We're going to end up foiling because this is going to be r plus 18. So we're going to have our math here. We have r squared plus 24 squared equals r plus 18 squared. So then rewriting this, 24 squared is actually 576. And then I'm going to rewrite this r plus 18 twice so that I can FOIL. So what stays on the left, kind of leave that alone for now. First, r times r is r squared. Outsides, r times 18 is 18r. Insides, r times 18 is 18r. Last, 18 times 18 is 324. So then if we go ahead and clean that up a little bit, can't really do anything on the right side, left side yet. 18 plus 18 is 36 plus 324. Well, again, this is nice. Our r squareds cancel. So we get 576 equals 36r plus 324. We're going to subtract the 324 to get 252 equals 36r, which means r equals 7 once we divide. So it's a lot of work, but again, those are the most challenging ones. And just remember, you got to use these parentheses so you know the FOIL there. And hopefully you guys remember foiling from algebra. Let me know if you need help with that. Here, we need to find the value of x. We see that they share a common point, and we see that these are both 90-degree angles right here. So we know they're both tangents. So we just have to set them equal to each other. So we have x squared equals 9. Well, to solve for this, the opposite of squaring is taking the square root. So you would get x equals 3. But we know whenever we take the square root of a number, we could get positive or negative 3. Because positive 3 squared is 9, negative 3 squared is also 9. And since it's just x squared, we need to have both. I won't be too picky about that, but technically your answer is plus or minus 3. And then that wraps up our notes for section 10.1. Here is your homework assignment. Let me focus this a little bit. There's your homework assignment, so take a picture of that, write that down real quick, and let me know if you have any questions.